Okay, 你好, let's get started. So today, lecture number 7, compaction, curing, and fresh property. Okay, so when we design the concrete, we need to cast the fresh concrete into place, like either in a formwork, and then we need to compact the concrete. Okay, the reason for compaction is to make the concrete homogeneous, and also get rid of these air bubbles, and also make sure the concrete will fill every corner of the formwork and all around the rebar. Okay, so that's compaction. Okay, curing is more complicated. Let's begin the lecture. So the purpose for compaction is to, first of all, to eliminate the voids and the entrapped air, okay, because otherwise the strength will be lower, the concrete will also be less durable. Also to ensure the concrete will fill every corner of the formwork and also go around the reinforcement. So that's when concrete hardens, we have decent strength. Okay. So that's the two purposes for compaction. We could either use external vibration, okay, or we could use internal vibration, okay, depending on the size of the job. Okay. When concrete has less workability, for slump less than 2 inch or even less, okay, we need to be careful about fully compaction for the concrete. However, if we have over vibration, the concrete may segregate, or so-called bleeding, okay, or even loss of entrained air. So entrained air is the good air to ensure the concrete has good durability. So under vibration or over vibration is not good. Okay. For small job, we could use steel rod, such as cast cylinder. We use a steel rod to consolidate the concrete. Okay. For large job, we could use vibration table or vibration rod. Okay. Maybe we can see from here. This is the external vibration table. We put the concrete on top of the table and vibrate and consolidate it. We could also use the internal vibration rod to consolidate the concrete. Okay. However, not all concrete need vibration. Okay. For example, self-consolidating concrete or self-compacting concrete does not need any type of vibration. Okay. Sure. So this is vibration. Then look at the curing. There's two purposes for curing. One is to prevent the loss of moisture from concrete. The reason for that is because the chemical reaction in concrete, we call that hydration. So hydration is a chemical reaction between cement and water. Okay. So without water, hydration will stop. So actually, the internal relative humidity RH should be larger than 80%. So less than 80%, the chemical reaction will stop. Second reason for prevent loss of moisture from concrete is to reduce the shrinkage of concrete. Okay, so we have dedicated lecture on shrinkage and creep of concrete. Okay. But when concrete lost moisture, it may shrink, and too much shrinkage, the concrete will crack. Okay, so that's another reason we need to prevent loss of moisture from concrete. And the second goal for curing is to maintain a favorable temperature for a certain time. Okay, the temperature could not be too low. Okay, otherwise the concrete will freeze. We call that freeze and thawing damage. And also the temperature cannot be too high. Then we could have problems such as flat set, plastic shrinkage, or other durability issues such as delayed entry guy formation. Okay, so the temperature should be moderate. So curing need adequate moisture, water. Also, the temperature cannot be too high or too low, and also the time for curing should be long enough. Typically, I will say at least 5 to 7 days. The longer, the better. Okay. If any of these three factors are missing, then the desired property may not be achieved. So the effect of adequate curing on hardened concrete property, including the strength, permeability, the resistance to abrasion, resistance to freeze-thaw damage, and also shrinkage and creep. Okay, so all of these properties is affected by curing process in concrete. Right. And here shows how the curing time, okay, and its effect on strength of concrete. Okay. For all the four concrete, the mix design is the same. The only difference is how much time we put the concrete under moisture curing. Okay. When we put the concrete in air entire time, which means after we demold the concrete, no moisture curing, then the strength will stop going higher at early age, and the final strength will also be lower. Okay. The longer we keep the concrete in moisture curing, the strength will keep going up. Okay. The reason for that is with increased curing time, the concrete will dry out later, so we have longer time for hydration to go on. We have more hydration products, so that will increase the degree of hydration and also increase the strength of concrete. And here shows how the curing time will affect the strength of concrete. So again, all the four concrete, the four lines, has the same mix design. The only difference is curing temperature. So the red line is the control mix, which is the concrete is casted and also cured at 23 degrees Celsius. Okay, that's the standard curing temperature. Okay. The blue line is we cure at 32 degrees Celsius, and also cure at the same temperature. Okay. So compared with control mix, the concrete cured and casted at higher temperature will have higher early age strengths, but lower later age strengths. Okay. When we reduce the curing and casting temperature, such as this green line and this purple line, the earlier age strengths will be lower, but later age strengths will catch up. Okay. So the reason for that is when we increase the hydration temperature, the hydration rate will increase. So at early age, we have more hydration product. As a result, the strength will be higher. On the other hand, when we have faster chemical reaction, the hydration product tend to be less uniform. We have less homogeneous hydration product. So that will result in lower final strength. Okay. So to summarize, the effect of temperature on curing, the higher temperature, the faster the curing, and the best temperature is the room temperature. So that's very convenient. The strongest concrete is made at temperature just above freezing temperature, okay, around 40 degrees Fahrenheit. But that is not very practical in most cases. Okay. If the concrete freezes during the first 24 hours or first a week, it may never be able to attain its original properties. So we need to keep the concrete above freezing temperature at early age at least. If the temperature is very high, about 120 degrees Fahrenheit, that may also cause damage, okay? Because the concrete may set too fast. Okay? And also a potential problem, we call that DEF. DEF is for delayed ethylene glycol formation. And we know ethylene glycol is one of the hydration products from chemical reaction of CEE688, right? CEE688 is one of the compounds in cement. So delayed ethylene glycol formation is one of the potential sulfide attack in concrete, which means we have formation of ethylene glycol after concrete hardens. That only occurs when the temperature, the curing temperature is very high. We could also do high temperature curing. So high temperature together with high pressure, also we call that autoclave. So that will change the chemical reaction totally. We have totally new hydration product. Okay. So let's look at typical curing method for concrete. You may look at how construction workers cure the concrete on job site. Okay, so the first time is we supply additional water with either pounding or immersion of the concrete underwater. Okay, so that will provide extra water on top of the concrete. Okay. However, that will not change the water to cement ratio because the concrete is fully casted in place. Just provide extra water on the top layer, you will not change the water to cement ratio. So keep that in mind. So actually you can even cast the concrete underwater without changing the water to cement ratio. Okay. So this type of curing is the very best for concrete. Okay. Because by providing extra water on top of the concrete, we can ensure every part of the concrete is fully saturated. So hydration will go on in every part of the concrete because it is fully saturated. Okay. So the second curing method is to seal the concrete by either use plastic sheets or could use membrane forming curing compound. Like showing this picture here in the bottom. So the worker here spray is not water, it is membrane forming curing compound. It just forms something like a plastic sheets. So moisture will be sealed underneath the plastic sheets. However, not every part of the concrete can be guaranteed to be fully saturated. For example, the top part of the concrete may still be dried because the curing membrane may not be very effective. But compared to the first method, it is more convenient and lower cost because we do not providing actual water as in the first method. But the drawback is it's not as effective as the first type due to only part of the concrete is saturated. So it cannot entirely prevent evaporation. For this type of curing, if the concrete has lower water cement ratio, the concrete may suffer so-called self-desiccation. Okay, so self-desiccation is drying off the concrete because the water cement ratio is so low. So hydration will consume a lot of water. If the water to cement ratio is very low, I will say less than 0.4, okay, then the pores inside the concrete may be dry due to hydration. Okay, so that may cause the concrete to shrink, and that type of shrinkage is called autogenous shrinkage. Okay, We'll talk about this more when we talk about shrinkage of concrete. Right, so that's the second type of curing. The third one is we cure the concrete with live steam. We call that steam curing. So the temperature will also be high. Or we can using heat coins or other heating method to ensure the concrete temperature will not be dropped below the freezing temperature. Okay, so that is the special curing method. Let's look at steam curing. So for steam curing, we put the concrete into the special steam curing chamber. Okay, and inside the chamber, we can control the temperature. Here shows the temperature inside the steam curing. Okay, and when we put the concrete inside the curing chamber, the temperature is not suddenly increased to certain level, like a 60 degree, because if the temperature is increased too suddenly, the concrete may crack or change the chemical reaction. So we need to slowly increase the curing temperature, like in this second stage. Okay, so that stage take about 2 to 3 hours. Okay, but we also have the first stage, which is initial delay. After we mix the cement with water, we need to let the concrete to hydrate for several hours before we put in the steam curing. And then inside the curing chamber lasts around 6 to 12 hours, and then we slowly decrease the temperature before we take the concrete out. And here shows how different the curing temperature and also the time period, we call that delayed period, before we do the steam curing, how that two factors affect the strength of concrete. Okay. Right. And here shows how the curing temperature affect the strength at 1 day, which is the blue line, and also the 28 days. Okay. So similar to the traditional curing temperature, we increase the curing temperature, early day strength will be higher, but 28 day strength will be lower. Okay, again, for the same reason. Higher curing temperature will increase the hydration speed, so we have higher early strengths. But it will also generate non-uniform distribution of hydration product, and that will result in lower final strength. Okay, and again, if the curing temperature is above certain level, that may cause delayed ethylene guide formation. Okay, the high temperature actually will dissolve the ethylene guide in concrete, which is formed at early age due to this high temperature, and then when temperature drop down, ethylene guide will be formed again in other part of the concrete, and because ethylene guide formation will cause expansion of solid volume, so concrete may crack due to this delayed ethylene guide formation. Okay, we're gonna talk about this more. We talk about sulfate attack in concrete. For autoclaving, the curing temperature is very high, above the boiling temperature of water. But because the temperature, the pressure is also very high, so the water in concrete will not actually boil. Okay, so high temperature and high pressure. So then we're gonna have new hydration reaction and new hydration product, only used for precast industry, because the autoclaving chamber is very big. Okay, we cannot bring that to the field. So 28 strength of concrete can be achieved within the first 24 hours. So very fast turnaround time. And also because we have totally new hydration product, the concrete will have better sulfate resistance and also less shrinkage and creep. Okay. So for curing, the tips are we need to provide a lot of water for long enough time. The longer, the better. Do not let the concrete dry, at least for the first 5 to 7 days. Remember, dry concrete is equal to dead concrete, which means there's no hydration will goes on. Okay, all the chemical reaction will stops when the inside relative humidity less than 80%. Okay, if the concrete dries out, we cannot revitalize the concrete after it dries, even we put the concrete back into water. So remember that. For temperature, moderate temperature is the best. Room temperature around 75 degree Fahrenheit, 23-24 degrees Celsius will be the best. Okay, too low the temperature, below the freezing temperature, the concrete will freeze. Okay, temperature is too high, we may have delayed nitrogen gas formation, flash set, and so on. Okay. If the concrete has flash or slag, it will require longer curing because flash and slag, we call that pozzolanic materials. And for pozzolanic reaction, it requires longer curing time because that reaction is slower compared to hydration of cement. All right, so that is compaction and curing. Any questions so far before we discuss the early age properties? Okay. So in early age property, we discuss workability and concrete rheology and how we can do the slump test for concrete and how we check the setting times. And also how we measure the air content of concrete. Okay, so we call that early age properties. Early age means right around time concrete set, around the first day also. So what is rheology? Rheology is a science dealing with deformation and the flow of materials under stress. Okay, typically a rheological curve is a curve of shear rate versus shear stress of materials such as concrete. And the workability is defined as the amount of energy, mechanical work, required to produce a fully compacted concrete without segregation and bleeding. Okay. Consistency, we talked about the word before, is defined as how easy the concrete to flow, and it is quantified as the slump test. And the cohesiveness is defined as the tendency for concrete to bleed or segregate. Okay. So let's look at this definition each. Formal rheological treatment of concrete is very, very difficult. Okay, for my PhD study and also the first 8-10 years work at UH, one of my research focus is on rheology property of concrete. So fresh concrete is not a classical colloid, okay, but it is a dense slurry, okay, with sand and also the large aggregate. We call that rock, okay. The rock has 1 inch or more in size. Okay, and we have cement paste within concrete is fluctuated system with micrometer size cement paste. Okay, cement paste particle is suspended in water, and don't forget we have chemical reaction goes on between cement and water. And particle size is very thin. The layers between sand grain and rocks is very, very small. Could be small as 100 micrometer, which is 0.1 millimeter. Okay, and also within the cement paste, we have entrained air and also entrapped air. Okay, and here it said conventional cement paste in concrete is 1 cubed single flock. Okay, we have sticky contacts between cement grain and a lot of excess water to convey a fluidity of the concrete. Okay, and for water reducer and superplasticizer can deflacculate the system. Okay, but the effect is only temporary. Okay, so that will increase fluidity of concrete. Okay. And the reason for deflacculation is from the steric effect, as we discussed in the lecture of chemical admixtures. Okay. And it says the net effect of superplasticizer and rheology of cement paste is change the cement paste from Bingham models to from Bingham bodies to Newtonian fluid. Okay, so what is Bingham fluid and what is Newtonian fluid? Okay, we're going to discuss in a moment. For concrete, it is even more complicated than cement paste. Okay, what is, here shows the basic rheology. So let's say we have a liquid phase and want to shear the materials by using shear force. Let's say we have force here and the cross-section area is A, right? And the shear speed is defined as V, the velocity. Okay. If we consider the layers of liquid, right, and the shear stress, we use tau. Tau is the shear stress is equal to the shear force F divided by the cross-section area A. And the shear rate is, we using this, okay, is defined as the shear speed V over Y. Y is the distance between two layers of liquid. And the coefficient of viscosity is defined as the shear stress tau equal to the shear rate. Okay, and this is for Newtonian law of viscous flow. And these two figures shows the difference between Newtonian fluid and the so-called Binghamian fluid. Okay, so we have a curve of shear rate versus shear stress. For Newtonian fluid, as soon as we have shear stress, we start to have rate of shear. Okay, and also the slope of the curve is constant. As we can see, we have a straight line in the Newtonian fluid, and the slope of the curve is the viscosity. Okay, but for Binghamian fluid, okay, at zero shear stress, we have zero shear rate. Okay, actually, when the shear stress is less than a so-called yield stress, which is defined as tau zero. So when the shear stress is less than tau zero, there's no moving of the liquid. So the shear rate is zero. As we can see from here, only when the shear rate is larger than the shear stress, yield stress tau zero, then the shear rate becoming to increase. And after that, the slope is also constant. which means we have a straight line. So we call that type of fluid Bingham fluid. Okay, the shear stress tau minus tau zero. Again, the tau zero here is defined as yield stress. When the shear stress less than the yield stress, there's no shear movement of the liquid. Okay, and the slope is called viscosity. All right. So again, the intersection of the line with the y-axis, which is the shear stress, we call that yield stress or tau zero, and the slope of the curve for Bingham model is called plastic viscosity. Okay, for cement paste and concrete, we could think it follow a Bingham model, more or less. All right. However, in a real situation, okay, the concrete and cement paste will show behavior we call like sexotropy. Okay, so look at these two curves. Look at the curve A first. Okay, so this is again the shear rate versus shear stress. The arrow shows, initially we increase the shear rate, okay, and then the slope becomes smaller and smaller. Okay, it is not a straight line. When we increase the shear rate, and then we slowly reduce the shear rate, okay, and the curve will be something like this. So the slope will become smaller and smaller. And if you go back to the same yield stress here, B is a little bit more complicated. Okay, because the up curve and backwards curve will not come back to the same point. Okay. Right. So sexotropy is decrease of apparent viscosity. Apparent viscosity is the ratio at any point in the curve, the ratio of the shear stress versus the shear rate. For example, for this point, the apparent viscosity is the shear stress at that point over the shear rate at that point. So that is apparent viscosity. So apparent viscosity will decrease under the shear stress, and followed by gradual recovery when the shear stress is removed. Okay, and we can see the effect is time dependent. Okay, depending on whether we increase the shear rate or decrease the shear rate. Okay. For case A, we call that true sexotropy, because the upwards and backwards, okay, come back to the same point. And for the case B, we call that pseudo sexotropy, because it is not fully reversible. Okay. So when we increase the shear rate to this point, and then we reduce the shear rate to 0, and the shear stress does not come to the same point. Okay, and we call that pseudo sexotropy. Okay, for concrete, it will somehow show one of these two behavior. Right. So fresh concrete behave crudely, as Bingham body, okay, with a definite yield stress, tau zero, and reasonably consistent plastic viscosity. Okay, that means the slope of the curve is kind of like a straight line. Okay, because the plastic viscosity can be seen as the basic slope of the curve. Okay, for this curve, the slope is changing. Okay, but we can simplify as a constant slope of curve. Okay. A typical value for yield stress is around 1000 Pascal for normal concrete, but for concrete which is very flowable, it could be as low as 50 Pascal. Okay. Typical value for plastic viscosity, which is again the slope of the curve, is around 100 Pascal second. Okay. For flowing concrete such as SCC, the yield stress could be much lower. Okay. And also plastic viscosity could also be much lower. And the last sentence here says, the structure breakdown observed in cement paste at a higher shear rate is not a factor in concrete. So that basically tells us, because within the cement paste within concrete is always sheared very thoroughly, because the distance between the aggregate is very small in concrete. So the cement paste is always sheared very well. Okay, but for cement paste, because cement paste has no aggregate, then the shear will be much less as the cement paste in concrete. So the concrete flow are hugely affected by amount of aggregate, because amount of aggregate will affect the distance between the two aggregate, thickness of the cement paste layer. And the slump instead is a crude measurement of plastic viscosity of concrete. Okay. But some other researchers said slump is actually a measurement of yield stress, which is the tau zero, the intersection between the curve and the web cell. And if we do the vibration, that will reduce the yield stress and the plastic viscosity of concrete. So that is a dynamic process for both the yield stress and the viscosity. For measurement of rheology, there's many different types of rheometer. Because rheometer is machine to measure the rheology of materials. For concrete, this is one example of concrete rheometer. In the UH concrete lab, we have so-called ICAC concrete rheometer to measure the viscosity and the yield stress of concrete. For cement paste, we have another rheometer. We call that boring rheometer. That's rheometer can measure the viscosity of concrete, asphalt, and other type of materials. All right, here just show an example of studying concrete rheology here at UH. This is done several years ago. The project is to optimize the mixed proportion based on the packing density of aggregate and also rheological model of concrete. Okay, so my graduate students try to optimize the mixed design for self-consolidating concrete using our local aggregate. Okay, so before the work, we just used the mixed design borrowed from other places, because in other places they use different type of aggregate. Okay, the property of aggregate here at Hawaii is totally different from the aggregate in places such as Illinois. So when we just use the same mix design, the concrete does not flow at all. Okay, as we can from here, the concrete is very, very steep. Okay, that's not enough cement paste because our Hawaii airgrid is very porous. So that means we need more cement paste to cover the surface of airgrid. And also the packing density of our local airgrid is lower. That also translates into more requirement for cement paste. So after the optimization of this mix design, the concrete become flowable again. Okay, as we can see from here. So that work is based on measurement of rheology and also modeling of concrete rheology. Okay, for example, this is a viscosity model based on Krieger-Doppler equation. So in that equation, the apparent viscosity of concrete, which is here, is equal to apparent viscosity of cement paste, and also is affected by the volume fraction of airgrid. The phi here, the phi m is the maximum packing density for certain type of airgrid, and also this is called intrinsic viscosity of airgrid, which is depending on the shape and also the porosity of airgrid. Okay. So using this equation, we can kind of predict the apparent viscosity of concrete based on the viscosity of cement paste and also the property of airgrid. This is another model for yield stress of concrete. This is yield stress of concrete as a function of yield stress of cement paste. Okay, and also the volume fraction of airgrid and as well as the maximum packing density of airgrid and also a certain type of coefficient. So using that equation, we can predict concrete yield stress based on yield stress of cement paste and airgrid. So together with the modeling and also the measurement of concrete as well as cement paste rheology, we can better design the concrete. Okay. Factors affecting concrete workability. The most important is how much water is in the concrete. Okay. And also how much airgrid we have, the particle size, the particle shape, the gradation curve of airgrid, as well as the packing density of airgrid. Okay. The time of the day, even the temperature, because the time and temperature will affect hydration. Okay. So all these factors will affect the workability of concrete. We mentioned about segregation and bleeding before, and here is a formal definition for these two words. Okay, so segregation means the settlement of coarse airgrid, the largest stone in the concrete, to the bottom of the concrete before the concrete is set. Okay, after the concrete is set, of course, the airgrid cannot settle. But before concrete is set, when the viscosity or the yield stress of cement paste is too low, the airgrid may settle to the bottom. So the reason for segregation include the density of airgrid is too high, the size of the course is too large, or we have too wet or too dry mix, okay, or we do not have enough sand. So bleeding, yeah.
Question. On the field, I got to see something they call it like honeycombing. Is that what it is?
Honeycombing means we have very big air voids inside the concrete. Like the air voids in the size of 0 centimeter, couple of inch. The big voids in concrete. So that will greatly reduce the strength and also durability of the concrete. So we call that honeycombing. So honeycombing is due to the compaction is not very good. Okay. All right.
Thank you.
So segregation means the settlement of coarse aggregate to the bottom of the concrete. Yeah. So bleeding means the separation of water from the cement. Okay. The water can go on top of concrete, or the water can trap beneath the aggregate, or trapped behind or beneath the reinforcement. Okay. So too much bleeding will reduce the strength of concrete, reduce the bonding between the aggregate and the cement paste, and also reduce the bonding between the reinforcement and the concrete. Okay. So to avoid bleeding, we could either increase the amount of entrained air, or we reduce the water to cement ratio if we can. Okay. Or we increase the hydration rate. Okay. Use more pozzolans can also be helpful, or we can use fibers. Fibers can also make the concrete more stiff and reduce the bleeding. Right. So here is the famous slump test. I think many of us has done that before. So this is the slump, so-called slump cone. Okay. So the size is 4 inch in the upper opening and 8 inch in the bottom opening. The height is 12 inch. So we put the cone on the floor and we fill the concrete into the cone with 3 layers. Okay, we fill the concrete to the first 1/3, and then we consolidate the concrete with the steel rod 25 times, and then we fill the second 1/3 layer here, and then we consolidate the concrete for another 25 strokes, and then the third layers. Okay, and then we lift up the cone. We have a handle here, slowly and vertically, and then we let the concrete to fall under its own weight. So the slump is how many inch the concrete slump after we lift up the cone. Okay, so slump is a measurement of consistency. Okay, remember, but for the same mix, it can also tell us about the workability of concrete, or how much energy is needed to fully compact the concrete. Okay. But a slump is not suitable for too wet or too dry mix. If the concrete is too wet or too dry, we can use some other test, but not a slump test. Okay. Again, here shows the procedure for a slump test. So three layers, and for each layer we do 25 strokes using the steel rod. Then we lift up, and then we let the concrete slump, and we measure how many inch the top surface of the concrete slumped. And here shows some of the lab results for a slump. Okay. So we measure how many inch the concrete slumped from here to the top of concrete. Okay, so different concrete with different water to cement ratio, without superplasticizer SP, with silica film or not. Okay, so we can have different slump value. If the concrete is very flowable, such as SCC, so SCC is for self-consolidating concrete, then we cannot measure the slump. Okay, so instead of the slump, we measure the diameter of the concrete pipe after concrete stop flowing. Okay, we call that slump diameter. if the concrete is too stiff, when we measure the slump, it shows 0 slump. Then we should use the so-called VB test. Okay. So VB test is for very dry mix. The specimen is similar to slump. Okay. So we put a slump cone on a vibration table. Okay. And we cast the concrete using 3 layers, same as the slump test. And then, the concrete is within a certain container with this size. Okay. Also, we have 9-inch diameter glass plate. Okay. So when we vibrate the table, the glass plate will push the concrete into that container, and we count how many seconds for the glass plate to compact the concrete into that container. Okay, so this is for very stiff concrete mix. Okay, we use VB test instead. Okay. This is air content. Yeah.
Why will you use that really stiff concrete? What applications?
Sometimes we want really stiff concrete. For example, when the water cement ratio is very low, the mix will be very stiff. Okay, when we want very high strength, or when the concrete has steel fiber in it. Okay, when you put fibers in the concrete, the mechanical property will be very high, the toughness will be high, strength will be high, but the concrete will be very hard to mix, very stiff.
Because I seen the self-consolidated concrete, and that's for hard to reach spaces. But I have never seen like this one. I don't know.
Yeah, we do in some situation have a very stiff concrete. Okay, so that need a special compaction.
Okay.
And also special test. Okay. All right. So here shows the air content test. Inside the concrete, we have a small percentage of air by volume, typically around 1 to 2%. But for air in training concrete, we have a higher percentage of air, maybe 4 or 5% by volume of concrete. Okay, and this is air content test. There's 2 types of air content test. This is the first one, volumetric method. Okay. So the idea of the test is very simple. Okay, so we can see we have bottom part. The bottom part has concrete, so we put the concrete in the bottom section and we consolidate it. Okay, and then we put the top part, but the top part has no concrete. So, but we put the water in the top part and we let the water penetrate inside the concrete. So the water will fill the air voids inside the concrete. And by measure how much water level goes down in the top part, we measure how much water get into the air of the concrete. Okay, so that's the air volumetric method to measure the air content for concrete. We could also use the second type. The second type is called pressure method. Okay, so pressure method, the air content is determined by observing change in volume of concrete with a change in pressure. Okay, still, the first step is to fill this container with concrete. 3 layers, 25 strokes using steel rod. Okay, so we fill 3 layers of concrete into the container, and then we put the lid on top of the container. We also add water to fill any air gap between the top surface of the concrete and the lid. And then we slowly increase the pressure. As we can see, we have valves here. So we increase the pressure on the concrete and we measure the volume change of the concrete. Right. So under this level of pressure, the volume change of concrete is only due to volume change of air. Okay. The change of volume of solid, including cement and also liquid, such as water. So the volume change for solid and liquid is very, very small. So the volume change is due only to the air inside the concrete. So based on that, we can estimate the air percentage for concrete. However, this type of method is not valid for lightweight concrete, because for lightweight concrete we use lightweight air weight. Okay, so such as here. So here shows the cross section of lightweight air weight or LWA. As we can see, inside the air weight we have a lot of air. Okay, if we use a lot of lightweight air weight in the concrete, and when we do the pressure type of air testing, the air inside the air weight will also be compressed. So that will overestimate the percentage of air in concrete, because we only care about air inside the cement paste and not care about air inside of air weight. So remember, this method, the pressure method, is not valid for lightweight concrete with lightweight air weight. All right, the setting time test. I think we talked about this before for cement paste. Okay, for cement paste or mortar, we use the VCAP needle. Okay, we measure how much penetration in millimeter the needle can penetrate the mortar test. For concrete, it's pretty much similar, but we use this penetration apparatus. Okay, so this machine can measure how much pressure and how much psi take the spindle to penetrate the concrete samples. So we just use this penetration apparatus around every 5 minutes or 10 minutes. Okay, for many different test points, we can connect the points as the curve. The initial setting time, which is corresponding to 500 psi, psi is pound per square inch, is the initial set time. And final setting time is the time when the penetration corresponding to 4,000 psi or 4 ksi. Okay. All right. And then let's look at the rheology of fresh concrete. From the beginning to initial site time to final site time. Okay, so initially, let's say we have a certain amount of yield stress, and the plastic viscosity is around 100 Pascal. Okay, so that is the slope of the Bingham curve. Okay. All right. So when concrete hydration, we have more and more hydration product, and hydration product will try to connect each other. That will increase both the yield stress and also the plastic viscosity, as you can see here. So the yield stress increase, the slope of the curve, which is the plastic viscosity, also increase. All right. So when the concrete almost set, the particles will connect each other. Okay, we have transition from full fluid to semi-solid. Okay, so we can see the yield stress further increase, and so does the plastic viscosity. Okay, at the site time, the continuous movement is no longer possible. Okay, so the Bingham model is no longer applicable, and this total mass will change from the liquid to a viscoelastic solid. Okay. We could have elastic response, but this is due to elastic strain and also creep, but there's no shear rate and shear stress. All right. Here talk about force set and flash set. Okay, this is different from initial and final set time. Okay, so concrete is different at short time after mix. Okay, but if it is force set, the fluidity can be restored by mixing, because force set is occurs when we have formation of gypsum. Okay, and gypsum is not very hard. When we do remixing, the concrete can become fluid again. For flat set, it is caused by formation of a lot of AFM, okay, or action guide. Okay. And if that's the case, the fluidity cannot be restored by further mixing of the concrete, okay, because we have a formation of AFM or action guide. If that's the case, the concrete will set. Remixing the concrete is not helpful. Okay. And the flat set could be either caused by the alkali sulfate content is high, or the added gypsum content is not enough. Okay, then we have a formation of AFM. All right. So in this class, we talk about compaction and curing, and then we talk about fresh properties, like how to measure the set time, rheology of the concrete, air content test, the slump test, and so on. Okay. All right. Questions?